you exist. Right now, reading this, breathing, thinking. Every atom in your body carries a history, where it's been, what it's done, the precise quantum state that makes you, you. The calcium in your bones was forged in the heart of an exploding star. The iron in your blood cycled through multiple stellar generations before finding its way into your veins. The carbon that forms the backbone of every protein, every strand of DNA, every thought firing across your neurons, it remembers its journey through the cosmos in a way that goes deeper than memory as we understand it. But there's something in the universe that might have the power to erase that history completely. Not metaphorically, not philosophically. Actually, physically delete the information that describes your existence, as if you had never been, as if the atoms that compose you, the light that has reflected off your skin, the gravitational influence you've exerted on every object around you, all of it could be removed from reality's ledger. The universe might contain structures capable of performing the ultimate deletion, places where the past itself can be unmade. This isn't a question about memory or consciousness or the meaning we assign to our brief lives. This is about something more fundamental, more unsettling. The laws of physics, as we understand them, suggest that information cannot be destroyed. It can be scrambled, hidden, transformed beyond recognition, but never truly erased. The universe, according to quantum mechanics, keeps a perfect record of everything that has ever happened. Every interaction, every decay, every collision between particles leaves an indelible mark on the structure of reality, except perhaps at the edge of a black hole. The question we're pursuing tonight isn't whether black holes exist. We've seen them now, photographed their shadows against the luminous matter swirling at the precipice of oblivion. The question is whether they break one of the most fundamental principles in physics, whether they possess the ability to do what nothing else in nature can, permanently destroy information. And if they can, then everything we think we understand about the universe is wrong. Causality breaks down, the arrow of time becomes meaningless. The very notion that the present emerges from the past dissolves into incoherence. So before we descend into the mathematics of event horizons and Hawking radiation, before we confront the paradox that has consumed some of the brightest minds in theoretical physics for half a century, we need to understand what we mean when we talk about information. Because in this context, information doesn't mean what you think it means. When physicists talk about information, they're not talking about knowledge. They're not referring to the contents of books or hard drives, the memories stored in neural networks, the cultural heritage encoded in language and art. Those things matter, certainly, but they're not what's at stake here. What's at stake is something more primal. In the language of quantum mechanics, information is the complete description of a physical system. It's the full specification of reality at the most fundamental level available to us. Imagine you could zoom in on a single electron orbiting the nucleus of a hydrogen atom in your body. To fully describe that electron, you'd need to know its position in space, not approximately, but as precisely as the uncertainty principle allows. You'd need to know its momentum, the direction and speed of its motion. You'd need to know its spin, that strange quantum property that has no classical analog, a kind of intrinsic angular momentum that comes in discrete units. You'd need to know its quantum numbers, the set of integers that specify which energy level it occupies, the shape of its orbital, the orientation of that orbital in space. These aren't arbitrary labels we've assigned for convenience. They're fundamental properties, embedded in the fabric of quantum reality. They describe states that can exist and states that cannot. They determine how that electron can interact with other particles, what photons it can absorb or emit, whether it can participate in chemical bonds or remain isolated. Now extend that to every particle in your body, every electron in every atom, every quark in every proton and neutron, every photon of light that has bounced off your skin, every neutrino that has passed through you without interaction. The complete quantum state of all these particles, their positions, momenta, spins, energy levels, entanglement relationships with other particles, that's information in the physicist's sense. It's the universe's database entry for you. This description is staggeringly complex. The number of quantum states you could occupy is so vast that it defies human comprehension. If you tried to write down the complete quantum description of a human body, specifying the state of every particle, the number of bits required would dwarf the number of atoms in the observable universe. The information content of a person, in this technical sense, is effectively infinite from any practical standpoint. But here's what makes this more than an academic exercise in accounting. According to quantum mechanics, this information cannot be destroyed, ever, under any circumstances. This principle has a name: unitarity. It's one of the foundational axioms of quantum theory, as central to the framework as the uncertainty principle or wave-particle duality. Unitarity means that the evolution of a quantum system is reversible. If you know the complete quantum state of a system at one moment in time, and you know the laws of physics, you can in principle calculate the state at any future time. But the reverse is also true. You can calculate the state at any past time. Think of it this way. Imagine you're watching a movie of billiard balls colliding on a table. If someone showed you the film in reverse, you could still figure out what happened. The collisions would still obey Newton's laws, just playing backward. The information about the initial configuration is preserved in the final configuration. You could, with perfect knowledge of the final positions and velocities, reconstruct exactly where the balls started. Quantum mechanics takes this further. It says that no matter how complex the evolution, no matter how many particles interact, no matter how chaotic the system becomes, the information is never lost. It might become impossibly scrambled, spread across thousands or millions of particles in ways that make it practically unrecoverable, but it's still there. Encoded in the correlations between particles, in the phases of quantum wave functions, in the entanglement structure binding distant parts of the system. This is what the universe does. It takes information and transforms it, scatters it, encodes it in increasingly complex patterns. When you burn a book, you don't destroy the information it contained. You convert it into heat, light, and smoke. The information about which letters were on which pages is now encoded in the precise trajectories of billions of gas molecules, the wavelengths of photons radiating into space, the vibrational states of atoms in the ash. No human could ever extract that information and reconstruct the book, but quantum mechanics says it's still there in principle if you had perfect knowledge of every particle involved in the burning. This seems like an abstract principle, a mathematical nicety with no real consequences, but it has profound implications. If information cannot be destroyed, then the universe has a kind of memory. Not consciousness, not awareness, but a physical record of everything that has ever occurred, preserved in the quantum correlations between particles. The state of the universe right now contains, encoded within it, the complete history of how it got here. The Big Bang, the formation of the first atoms, the birth and death of countless stars, the emergence of galaxies, the chemical reactions that led to life on Earth. All of it is still accessible, in principle, from the current state of all particles in the cosmos. Causality depends on this. The reason the future emerges from the past in a lawful, predictable way is because information is conserved. If the universe could forget, if information could be destroyed, then cause and effect would break down. Events could occur without prior causes. Energy could appear from nothing or vanish into nothing. The laws of physics, which are built on the foundation of information conservation, would collapse. This is why the possibility that black holes might destroy information is so deeply threatening. It's not just one more interesting puzzle in physics. It's a potential crisis that strikes at the heart of how we understand reality. Because if a black hole can delete information, then the universe is not what we thought it was. The laws we've built up over centuries of observation and experimentation, the laws that allow us to predict eclipses, design quantum computers, understand the chemistry of life, all of those laws rest on the assumption that information is conserved. And black holes, as we'll see, seem to violate that assumption in the most spectacular way imaginable. The universe is vast beyond comprehension, roughly 93 billion light-years in diameter, containing 2 trillion galaxies, each with hundreds of billions of stars. Within this immensity, there are structures of astonishing variety. Planets where diamond rain falls from methane skies, neutron stars where a teaspoon of matter weighs 1 billion tons, magnetars whose magnetic fields could erase your credit cards from 1,000 miles away. But nothing in this cosmic menagerie is stranger, more extreme or more threatening to our understanding of physics than a black hole. We're going to spend time with these objects. We're going to understand what they are, how they form, what they do to the space and time around them. We're going to descend, theoretically at least, to the edge of the event horizon and peer into the abyss. We're going to trace the mathematics that predicts their existence and the observations that confirmed those predictions. But before we do any of that, before we talk about Schwarzschild metrics and gravitational redshift and the no-hair theorem, we need to sit with what's at stake. Because this isn't just about black holes, it's about whether the universe is fundamentally comprehensible. Whether the story of how you came to be, the chain of causation stretching back 13.8 billion years from the Big Bang to this moment, is actually written into reality, or whether it can be erased. If information can be destroyed, then you could have not existed, and the universe would have no way of knowing the difference. The atoms that compose you could fall into a black hole, and when that black hole eventually evaporates. Yes, black holes evaporate, more on that later. Those atoms would be gone, not just broken apart or transformed, but deleted. The quantum states that describe them, the history they carried, the causal chain they were part of, all of it removed from the universe's ledger. This is the information paradox, and resolving it has required some of the most radical ideas ever proposed in physics, ideas that challenge our basic intuitions about space, time, and the nature of reality itself. Ideas that suggest the three-dimensional world we inhabit might be a kind of hologram, a projection from a two-dimensional surface we can never directly observe. Ideas that force us to reconsider what we mean when we say something is inside or outside a region of space. The journey ahead is going to take us to the edge of human knowledge. We're going to encounter concepts that sound like science fiction, but emerge inevitably from the mathematics. We're going to see how a crisis in theoretical physics, the apparent contradiction between quantum mechanics and general relativity, has driven discoveries that reshape our understanding of what the universe is. And we're going to find that the answer to our central question, can the universe forget, is both more reassuring and more unsettling than you might expect. But first, we need to understand gravity, not as Newton understood it, as a force reaching across empty space, but as Einstein revealed it, as the curvature of space-time itself, the warping of the very fabric of reality by the presence of mass and energy. Because black holes aren't objects in space. They're regions where space-time curves so severely that it tears itself apart, creating boundaries beyond which the normal rules no longer apply. Let's descend into that geometry. Einstein's legacy gravity is not what you think it is. For centuries we understood it as Newton did, a force invisible and mysterious reaching across empty space to pull objects together. The Earth pulls on the Moon, the Sun pulls on the Earth, and somehow this influence propagates instantaneously across millions of miles of vacuum. It worked. The mathematics predicted planetary orbits with stunning accuracy, allowed us to discover Neptune by observing perturbations in Uranus's path, gave us the tools to navigate by the stars. But it left fundamental questions unanswered. What is this force? How does it travel? Why does it exist at all? Einstein gave us a different answer, one so radical it took decades for the full implications to unfold. Gravity, he said, is not a force, it's geometry. Mass doesn't pull on other mass across empty space. Instead, mass warps the structure of space and time themselves, and objects moving through this warped space-time follow the curves. Planets orbit stars not because they're being pulled by an invisible force, but because the star's mass bends space-time into a shape where orbital motion is the straightest possible path. Imagine space-time as a fabric, not a metaphor, but a genuine physical structure with curvature and topology. Now place a massive object on this fabric, a star perhaps, or better yet, a cluster of galaxies. The fabric doesn't just dimple slightly, it curves dramatically, creating a gravitational well that extends outward in all directions. The more mass, the deeper the well. The closer you are to the source, the steeper the walls. Now here's the crucial part. Objects moving through this curved space-time don't feel a force pulling them toward the massive object. They feel nothing at all. They're in free fall, weightless, following what's called a geodesic, the straightest possible path through curved space. When you watch the International Space Station orbit Earth, the E, astronauts inside aren't being pulled by gravity in the Newtonian sense. They're following the natural curvature of space-time created by Earth's mass, falling freely along a path that happens to be circular. This is general relativity. And it's not just a prettier way of describing Newtonian gravity. It makes predictions that Newton's theory cannot. It explains the precession of Mercury's orbit, a tiny anomaly that puzzled astronomers for decades. It predicts that light should bend when passing near massive objects, a prediction spectacularly confirmed during the solar eclipse of 1919, when stars appeared to shift position as their light grazed the sun. It predicts gravitational time dilation, that clocks run slower in stronger gravitational fields, an effect now measured with atomic clocks and essential for the GPS satellites that guide you to the grocery store. And it predicts black holes. The story begins in the trenches of World War I, an unlikely setting for one of the most profound discoveries in physics. Carl Schwarzschild was a German astrophysicist, already established in his field, with contributions to stellar spectroscopy and photographic photometry. When war broke out in 1914, he volunteered for military service despite being over 40 and in poor health. By 1915, he was serving on the Russian front, calculating artillery trajectories and managing astronomical observations for the military. In November of that year, Einstein published his field equations, the mathematical heart of general relativity. These equations are deceptively simple in appearance, relating the curvature of space-time, represented by a mathematical object called the Einstein tensor, to the distribution of mass and energy, represented by the stress-energy tensor. but solving them for any realistic scenario is brutally difficult. The equations are nonlinear, meaning solutions don't add up cleanly. They involve 10 coupled partial differential equations in 4 dimensions. Even Einstein himself hadn't found exact solutions for most cases. Schwarzschild received news of Einstein's theory while stationed at the front. And somehow, in conditions that defy imagination, freezing temperatures, the constant threat of artillery, the beginnings of the autoimmune disease that would kill him within months, he found an exact solution to Einstein's field equations. Not an approximation, not a numerical estimate, an exact closed-form solution describing the space-time geometry around a spherically symmetric, non-rotating mass. He sent his solution to Einstein in December 1915, barely a month after the field equations were published. Einstein was astonished. He had expected that finding exact solutions would take years, if it could be done at all. But here was Schwarzschild, working in a war zone, presenting the geometry of space-time around a star with mathematical precision. The Schwarzschild solution revealed something remarkable and disturbing. For any mass m, there exists a critical radius now called the Schwarzschild radius, with a specific value, RRS 2gmc2, where g is Newton's gravitational constant and c is the speed of light. If you compress a mass down to this radius or smaller, something extraordinary happens to the geometry of space-time. The Schwarzschild radius isn't large. For the Sun, it's about 3 kilometers. For Earth, it's about 9 millimeters. These aren't the actual sizes of these objects, of course. The Sun's physical radius is 700,000 kilometers. Earth's is 6,400 kilometers. The Schwarzschild radius is a hypothetical boundary that would only become relevant if you could somehow compress the Sun down to a sphere 3 kilometers across, or Earth down to a marble. At the time, no one thought this was physically possible. Stars are held up by internal pressure, thermal pressure from nuclear fusion in their cores, or electron degeneracy pressure in white dwarfs. The Schwarzschild radius was a mathematical curiosity, an artifact of the equations that didn't correspond to anything real. Even Schwarzschild himself didn't fully grasp the implications of his solution. He died in May 1916, killed by pemphigus, an autoimmune disease likely contracted during his service on the Eastern Front. He never knew that his wartime calculation had revealed the mathematical signature of the universe's strangest objects. For decades, the Schwarzschild radius remained theoretical, but in the 1930s, physicists began to realize that stellar collapse might not always halt at a white dwarf or neutron star. Subrahmanyan Chandrasekhar calculated that white dwarfs above 1.4 solar masses cannot support themselves against gravity. The electrons cannot provide enough pressure. J. Robert Oppenheimer and Hartland Snyder showed that massive stars, having exhausted their nuclear fuel, might collapse indefinitely, crushing themselves down past the Schwarzschild radius and beyond. This was the birth of black hole physics. Though the term black hole wouldn't be coined until 1967 by John Wheeler, the essential idea was clear by the 1960s. If you compress enough mass into a small enough volume, space-time curves so dramatically that it forms a region from which nothing can escape. Not matter, not light, not information. A one-way membrane in the structure of reality. The event horizon. 2 words that sound almost poetic, evoking the edge of perception, the boundary between known and unknown. But in general relativity, the event horizon is a precise mathematical surface with properties that violate every intuition we have about space and time. The event horizon of a Schwarzschild black hole sits exactly at the Schwarzschild radius. It's not a physical membrane, not a wall or barrier made of matter. It's a surface in space-time where the geometry becomes so warped that the roles of space and time flip. Outside the horizon, you can move freely in space, forward, backward, left, right, up, down. Time flows in one direction, from past to future, but your spatial coordinates are under your control. You can choose where to go. At the event horizon, this changes. The radial direction, the line pointing toward or away from the center of the black hole, becomes time-like. This is difficult to visualize because we don't experience anything like it in normal life. But the mathematics is clear. Once you cross the horizon, moving toward the center is no longer a spatial choice. It's as inevitable as moving forward in time. You can no more avoid falling toward the singularity than you can avoid tomorrow. Outside the horizon, time is a dimension you move through inexorably, while space is something you can navigate. Inside the horizon, the radial direction toward the center becomes part of time's arrow. The singularity at the center isn't a place you might go. It's a moment in your future that you will reach, as certainly as you'll reach next Tuesday. You can delay it slightly by accelerating outward, just as you might slow your movement through time by traveling at high speed. But you cannot avoid it. This inversion of space and time means that escape is not difficult. It's impossible. Not technologically impossible, not limited by the rockets we can build or the fuel we can carry. Geometrically impossible. The paths that lead outward don't exist inside the horizon. Every trajectory, every possible path through space-time leads inward and downward toward the singularity. Even light traveling at the universe's speed limit cannot escape. Photons launched radially outward from just inside the horizon simply hover there, suspended at the boundary, making no progress. Photons launched from deeper inside fall inward, despite their outward motion, carried by the flow of space-time itself toward the center. The escape velocity at the event horizon is exactly the speed of light. This isn't a coincidence. It's definitional. The horizon is located precisely where the escape velocity reaches C, where the curvature of space-time becomes so severe that even light cannot climb out of the gravitational well. Outside the horizon, rockets can escape if they achieve sufficient velocity. At the horizon, even light is trapped. Inside, nothing can escape because the very geometry of space-time forbids it. From the outside, the event horizon appears as a perfectly spherical surface, dark and featureless, defined by absence. It's the ultimate one-way boundary. Things can fall in, matter, energy, information, but nothing comes out. Not in classical general relativity, at least. As we'll see later, quantum mechanics complicates this picture in profound ways. But according to Einstein's equations alone, the event horizon is an absolute barrier, the point of no return. And here's where the information problem begins to emerge. Because if something crosses the event horizon, it's gone from the external universe. Not just hidden, not just difficult to observe, removed. An observer outside the black hole can never again interact with anything that fell in. They can't receive signals from it, can't measure its properties, can't extract any information about its internal state. From the perspective of the outside universe, the object has been deleted from reality. In classical general relativity, this isn't paradoxical. Information is simply locked away forever, inaccessible but still existing somewhere inside the black hole, falling toward the central singularity. But when we introduce quantum mechanics, when we start asking about Hawking radiation and black hole evaporation, this picture falls apart. The horizon becomes not just a barrier, but potentially a place where information is destroyed, where the quantum state of matter is erased from existence. But we're getting ahead of ourselves. before we can understand why black holes might destroy information, we need to meet one. Not a hypothetical mathematical construct, but a real black hole, one we can point telescopes at, one whose effects we can measure. We need to travel to the center of our own galaxy and confront the 4 million solar mass monster lurking there in the dark. Let's go meet Sagittarius A, 26,000 light-years from Earth, in the direction of the constellation Sagittarius. There is a region of space where stars move faster than they have any right to. Not just fast, violently fast, whipping around an invisible point at velocities that approach a significant fraction of light speed. These aren't distant galaxies receding from cosmic expansion. These are individual stars, bright enough to track across decades of observations, orbiting something we cannot see. That something is Sagittarius A, the supermassive black hole at the center of the Milky Way, our galaxy's dark heart. The name is almost playful, belying the object's nature. Sagittarius A was the designation given to a bright radio source detected in the 1950s, when radio astronomy was still in its infancy. The asterisk, pronounced A star, was added later to distinguish the compact, persistent radio emission from the larger, diffuse radiation filling the galactic center. But there's nothing playful about what that asterisk represents. It marks the location of an object containing 4.3 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. To put that in perspective, if you could replace our Sun with Sagittarius A, the event horizon would extend roughly 12 million kilometers from the center. Mercury, the closest planet to our Sun, orbits at an average distance of 58 million kilometers. The entire black hole, the region from which light cannot escape, would fit comfortably inside Mercury's orbital path, with room to spare. And yet, it would contain the mass of 4.3 million stars like our Sun. This is not a stellar mass black hole, the kind that forms when a massive star exhausts its nuclear fuel and collapses. Those black holes typically weigh between 3 and a few dozen solar masses. Sagittarius A is a supermassive black hole, a category of object whose formation mechanism is still debated. Did it grow from a stellar mass seed, consuming gas and stars over billions of years? Did it form from the direct collapse of massive gas clouds in the early universe? Did it result from the merger of many smaller black holes in the dense stellar environment of a young galaxy? We don't know with certainty. What we know is that nearly every large galaxy harbors one of these monsters at its center, and ours is no exception. For most of human history, we had no idea it was there. The galactic center is obscured by vast clouds of dust and gas that block visible light. When you look towards Sagittarius with your naked eye, you see the densest part of the Milky Way's band of stars, but the core itself is hidden. It wasn't until the 1970s, when radio and infrared telescopes could peer through the dust, that astronomers began to suspect something unusual lurked at the center. A compact radio source, persistent but variable, bright in X-rays, too energetic to be a cluster of stars, too compact to be a diffuse gas cloud. The breakthrough came from watching stars orbit this invisible point. Because while we couldn't see Sagittarius A directly, we could see its gravitational influence on nearby stars. And those stars told a story that was impossible to ignore. In the early 1990s, 2 independent teams began monitoring the motions of stars near the galactic center. One team, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, used telescopes at the European Southern Observatory in Chile. The other, led by Andrea Ghez at UCLA, used the Keck Observatory in Hawaii. Both teams employed adaptive optics, technology that compensates for atmospheric turbulence in real time, sharpening images to near theoretical limits. And both teams focused on the same question: what are these stars orbiting? The stellar motions they documented were extraordinary. Stars near the galactic center don't drift lazily through space like stars in our solar neighborhood. They race. Some complete their orbits in just a few years, which is astonishing when you realize these are full-grown stars, not planets, and they're orbiting something 26,000 light-years away. To track their motion required precision measurements repeated over many years, building up a catalogue of positions accurate to milliseconds. Angles so small, they're equivalent to spotting a golf ball on the moon from Earth. One star in particular became famous, S2, also known as S0 to 2 in the American team's catalogue. S2 is a bright blue star about 15 times the mass of the Sun. Its orbit around Sagittarius A is highly elliptical, bringing it as close as 17 light-hours from the event horizon at periapsis, the closest approach, and taking it out to about 1,000 times that distance at apoapsis. The orbital period is just 16 years. Think about that. S2 completes a full orbit around the galactic center in less time than it takes Neptune to orbit the Sun once. And S2 isn't some tiny asteroid or comet. It's a massive star, and it's moving at blistering speeds. At periapsis, S2 reaches about 7,150 kilometers per second, roughly 2.5% of the speed of light. Fast enough that relativistic effects become measurable. Fast enough that its orbital motion tests general relativity in a regime unavailable anywhere else. In 2018, S2 made its closest approach to Sagittarius A, and both teams watched with every instrument they could deploy. They were looking for specific relativistic effects predicted by Einstein's theory. Gravitational redshift, the stretching of light as it climbs out of the deep gravitational well near the black hole. The precession of the orbit, a slow rotation of the ellipse itself, caused by the curvature of space-time. Even subtle effects from the black hole's spin, frame-dragging the space-time around it. They saw them all. S2's light was redshifted exactly as predicted, its orbit precessed by the expected amount. General relativity passed every test. But more importantly, these observations allowed precise measurements of the central mass. By tracking S2's orbit and the orbits of dozens of other stars in the region, astronomers could use Kepler's laws to calculate what they were orbiting. The answer was unambiguous. 4.3 million solar masses concentrated in a volume too small to be anything but a black hole. No other object could be that massive and that compact. A cluster of stars would be far larger. A hypothetical ball of dark matter would collapse under its own gravity or be dispersed by stellar interactions. Only a black hole can contain millions of solar masses in a region smaller than a planetary orbit. The case was airtight. Genzel and Ghez shared the 2020 Nobel Prize in Physics for this work, and deservedly so. They had proven, beyond reasonable doubt, that Sagittarius A is a supermassive black hole. But S2 isn't the most extreme example. There are stars even closer, moving even faster, pushing the boundaries of what we thought possible in stellar dynamics. The S-star cluster, the population of stars within a few light weeks of the black hole, contains objects with properties that challenge our understanding of stellar formation and survival. How did these stars get so close? Stars don't form in the immediate vicinity of supermassive black holes. The tidal forces and radiation would disrupt the gas clouds. They must have migrated inward, perhaps scattered by gravitational interactions, perhaps captured from binary systems, where one star was captured and the other ejected at high speed. S4714 is particularly remarkable. Discovered in 2020, this star has an orbit so eccentric and so tightly bound that at periapsis, it reaches about 8% of the speed of light, 24,000 kilometers per second. At that speed, relativistic time dilation becomes significant. If you could somehow stand on S4714 during its close approach, ignoring the fact that you'd be vaporized by radiation and torn apart by tidal forces, your clock would run noticeably, slower than clocks far from the black hole. A year for you might correspond to a year and a few weeks for distant observers. S4714's orbital period is only about 12 years. Think about the acceleration required to whip a star around that quickly. The gravitational force it experiences at periapsis is immense, creating tidal forces that try to stretch the star along the radial direction and compress it perpendicular to that. The fact that S4714 survives these passages intact tells us something about stellar structure, about how much stress a star can endure before being torn apart. But not all stars are so fortunate. Occasionally, a star wanders too close to a supermassive black hole and crosses the tidal disruption radius, the distance at which tidal forces overcome the star's self-gravity. When this happens, the star doesn't simply fall in whole. It's shredded, pulled into a long stream of gas that wraps around the black hole multiple times before accreting onto the event horizon. These tidal disruption events produce spectacular flares of radiation, visible across intergalactic distances, as the stellar debris heats up during its final inward spiral. Sagittarius A has likely consumed many stars this way over its lifetime. In fact, the black hole has consumed a significant amount of mass, millions of solar masses worth of gas, dust, and stars over billions of years. Yet despite this, Sagittarius A is remarkably quiet right now. It's not actively feeding. There's no thick accretion disk of hot gas spiraling inward, no jets of relativistic particles shooting from the poles. The radio and X-ray emission we detect is feeble compared to what the black hole could produce if it were actively accreting. This is why we call it a starved monster. Sagittarius A has the gravitational reach to consume vast amounts of material, but there's not much material in its immediate vicinity to consume. The galactic center is dense compared to our solar neighborhood, but it's still mostly empty space. Gas clouds pass near the black hole occasionally, producing brief flares of activity, but sustained accretion is rare. The black hole sits in the dark, its presence revealed only by the stars orbiting it and the faint radio whisper of gas falling in at a trickle. This quiescence was actually advantageous when astronomers set out to photograph the event horizon's shadow. An actively feeding black hole would be surrounded by so much bright, chaotic material that the shadow would be obscured. Sagittarius A's starvation diet meant the region around the event horizon was relatively clean, making the shadow easier to detect. On May 12, 2022, the Event Horizon Telescope collaboration released an image that made headlines around the world. It showed a fuzzy orange ring with a dark center, about 50 micro-arc seconds across, superimposed on a simulation showing the expected appearance of Sagittarius A. This was the shadow of our galaxy's central black hole, resolved for the first time. The achievement cannot be overstated. Sagittarius A is small. Its event horizon spans about 24 million kilometers, which sounds large until you realize it's 26,000 light-years away. The angular size on the sky is roughly equivalent to seeing a bagel on the moon. To resolve such a small object required a telescope the size of Earth. The Event Horizon Telescope isn't a single instrument. It's a network of radio observatories scattered across the globe in Hawaii, Arizona, Chile, Spain, Antarctica. all observing the same target simultaneously at millimeter wavelengths. The technique is called very long baseline interferometry. Each telescope records the incoming radio waves along with precise timestamps from atomic clocks. Later, the data streams are combined, correlating the signals to reconstruct an image with resolution equivalent to a telescope with a diameter equal to the distance between stations. The technical challenges are staggering. The telescopes must observe in perfect coordination, often fighting weather and equipment failures. The data rate is so high that physical hard drives must be shipped to a central processing facility. It's faster to FedEx the drives than to transmit the data over the internet. The analysis requires sophisticated algorithms to reconstruct an image from incomplete and noisy data, essentially solving an inverse problem. What source distribution would produce the observed interference patterns? And the target itself is uncooperative. Unlike M87T, the supermassive black hole at the center of the M87 galaxy, photographed 3 years earlier and far more massive, Sagittarius A is relatively small, and the gas around it orbits quickly. Features in the emission change on timescales of minutes. During the hours of observation, the ring essentially morphs and flickers, making it harder to reconstruct a stable image. The team had to develop new techniques to account for this variability, effectively taking thousands of snapshots and averaging them in clever ways to reveal the underlying structure. What they found matched predictions beautifully. The shadow, the dark region in the center, corresponds to the photon sphere, the radius at which light can orbit the black hole. It's about 2.6 times larger than the event horizon itself, a consequence of how severely gravity bends light near the black hole. The bright ring is emission from hot gas orbiting just outside the photon sphere, Doppler boosted on the side moving toward us and dimmed on the side moving away. The image confirmed what decades of stellar orbit measurements had already established. Sagittarius A is a black hole, and it has the mass and size predicted by general relativity. But more than that, it provided a direct view of the space-time geometry near the event horizon. We could see the warping of light, the bending of photon paths into the characteristic ring shape. We could measure the shadow's size and compare it to theoretical predictions. Every detail matched. For the first time in history, we had a photograph, not just a theoretical model, but an actual image of a region of space-time so warped that light orbits like a planet. We had seen the edge of a black hole. So here it is, Sagittarius A, a proven supermassive black hole at the center of our galaxy, its existence confirmed by stellar orbits and imaged directly by a planet-sized telescope array. It sits there in the darkness, mostly dormant, occasionally flickering as wisps of gas fall past the event horizon and vanish into the abyss. And according to classical general relativity, everything that crosses that horizon is gone from our universe forever. Locked inside, falling toward the singularity, carrying its information with it into a region we can never observe. If a star falls in, the information describing its composition, its history, the quantum states of every atom it contained, all of it vanishes behind the event horizon and is lost to the outside world. This seems acceptable in a purely classical framework. Information isn't destroyed, it's just inaccessible. Somewhere inside the black hole, falling toward the center, the record of what fell in still exists. But we're about to introduce a complication, because black holes, it turns out, are not entirely black. They emit radiation, they evaporate, and when they do, the question of what happens to the information becomes acute and unavoidable. To understand why, we need to talk about Stephen Hawking and one of the most surprising discoveries in 20th century physics: the realization that black holes glow. Empty space is not empty. This is one of the most counterintuitive revelations of quantum mechanics, and it's essential to understanding why black holes are not the eternal prisons Einstein's equations suggest. When you look at a region of vacuum, true vacuum, devoid of matter and radiation, quantum field theory tells you something astonishing is happening. The vacuum seethes with activity. It fluctuates. Particle-antiparticle pairs blink into existence for fractions of a second before annihilating each other and vanishing back into the void. These aren't speculative entities, they have measurable effects. The Casimir effect, for instance, arises from quantum fluctuations of the electromagnetic field between closely spaced conducting plates. The plates restrict which wavelengths of virtual photons can exist in the gap, creating a pressure difference between the inside and outside that pushes the plates together. This force has been measured in laboratories with exquisite precision. The vacuum isn't passive emptiness, it's a turbulent sea of quantum activity, particles and fields fluctuating around their minimum energy states. Virtual particles, as they're called, exist in a strange liminal state. They're not real in the sense that you can detect them directly, or that they persist long enough to travel significant distances. They're better understood as mathematical artifacts of quantum field theory, temporary violations of energy conservation permitted by Heisenberg's uncertainty principle. The uncertainty principle tells us that dE x dt, or 2, where dE is the uncertainty in energy and dt is the uncertainty in time. This means that for sufficiently short timescales, energy can fluctuate wildly. A particle-antiparticle pair can borrow energy from the vacuum, pop into existence, and annihilate before the universe notices the energy debt. These fluctuations happen everywhere, constantly, throughout all of space. In ordinary circumstances, they have no macroscopic consequences. The particles appear and disappear so quickly that they can't interact with anything in the classical world. They're quantum noise, the irreducible jitter in the fields that permeate reality. But near the event horizon of a black hole, something remarkable happens. The extreme curvature of space-time changes the rules. Virtual particles can become real. In 1974, Stephen Hawking was working on the quantum mechanics of fields in curved space-time. He was trying to understand what happens when you apply quantum field theory, the framework describing how particles and fields behave, to the severely curved geometry near a black hole. This was uncharted territory. General relativity describes gravity and curved space-time. Quantum mechanics describes particles and fields, but no one had a complete theory that unified both frameworks. Quantum gravity remained and remains the holy grail of theoretical physics. What Hawking discovered, working in the approximation of quantum fields on a classical curved background, shocked him and everyone else in the field. He found that black holes emit radiation. Not from inside the event horizon, nothing escapes from there, but from just outside at the boundary where space-time curvature becomes extreme. The radiation emerges from the vacuum itself, a consequence of how the horizon interacts with quantum fluctuations. Here's the mechanism, at least in the most common heuristic explanation. Near the event horizon, virtual particle-antiparticle pairs are constantly appearing. Usually these pairs would annihilate almost immediately. But if a pair forms right at the horizon, it's possible for one particle to fall into the black hole while the other escapes to infinity. The particle that escapes is real. It carries energy away from the black hole. The particle that falls in has negative energy relative to the distant observer, and when it crosses the horizon, it reduces the black hole's mass. This is a simplified picture, and it's somewhat misleading if taken too literally. The real calculation involves quantum field modes and how they're transformed by the space-time geometry near the horizon. But the essential result is clear. From the perspective of a distant observer, the black hole glows. It emits thermal radiation with a characteristic temperature inversely proportional to its mass. The formula is elegant. T, or C3O, 8p b. Where is the reduced Planck constant? C is the speed of light, G is the gravitational constant, M is the black hole's mass, and K by B is Boltzmann's constant. The smaller the black hole, the higher the temperature. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, far colder than the cosmic microwave background, which is currently at 2.7 Kelvin. Such a black hole would absorb more radiation from the surrounding universe than it emits, growing rather than shrinking. But a smaller black hole, say one with the mass of a mountain, around 1 billion kilograms, would have a temperature of trillions of Kelvin. It would glow brilliantly in gamma rays, evaporating in a spectacular explosion over timescales accessible to human observation. And the smaller it gets, the hotter it becomes, the faster it evaporates, until in the final moments it releases its remaining mass energy in a violent burst. Black holes evaporate. They're not eternal. Given enough time, unimaginable stretches of time, longer than the current age of the universe by factors that dwarf comprehension. Even the largest black holes will radiate away their mass and disappear. For Sagittarius A, the temperature is fantastically small. With a mass of 4.3 million suns, Hawking's formula gives a temperature of about 1.4 × 10^14 Kelvin. That's 14 decimal places below 1 Kelvin. It's 100 million times colder than the cosmic microwave background. At this temperature, Sagittarius A emits essentially no detectable Hawking radiation. The black hole is currently gaining mass from absorbing stray photons from the CMB faster than it loses mass from Hawking radiation. It's growing, not shrinking, though the growth rate is negligible. This will change. The universe is expanding and cooling. The cosmic microwave background temperature decreases as the universe expands, dropping proportionally to the inverse of the scale factor. Eventually, in a few trillion years, the CMB will cool below the Hawking temperature even of supermassive black holes. At that point, more energy will leave via Hawking radiation than enters via absorption, and the black holes will begin their long, slow evaporation. The timescale is almost incomprehensible. For a black hole with the mass of the Sun, evaporation takes about 1,067 years. That's a 1 followed by 67 zeros. For comparison, the universe is currently about 1.410 years old. The black hole evaporation timescale is longer than the current age of the universe by a factor of about 10,000 trillion. For a supermassive black hole like Sagittarius A, the timescale extends to roughly 1099 years. But however long it takes, the process is inexorable. Black holes are not stable. They lose mass through Hawking radiation, and as they lose mass, they heat up. The evaporation accelerates. In the final stages, when the black hole has shrunk to a tiny fraction of its original mass, it becomes scorching hot, radiating furiously in the final countdown to oblivion. Imagine you could watch a solar mass black hole evaporate in fast forward, compressed into human comprehensible timescales. For most of its lifetime, the overwhelming majority of those 1,067 years, nothing appears to happen. The black hole sits in the darkness, imperceptibly dimmer than the surrounding vacuum, radiating photons so rarely that you might wait billions of years between emissions. The temperature is effectively zero, but as the mass decreases, the temperature rises, slowly at first, then faster. When the black hole has shrunk to 1/10 of a solar mass, the temperature has risen tenfold, and the evaporation rate has increased 100-fold. The process accelerates. By the time the black hole weighs as much as Earth, it's hot enough to glow in infrared. When it's down to 1 trillion kilograms, the mass of a large asteroid, it's radiating invisible light, glowing like a star. At 1 billion kilograms, it's radiating in X-rays, blazing with the luminosity of a supernova. And then, in the final microseconds, the black hole pours out its remaining mass energy in a cataclysmic flash. The temperature skyrockets toward infinity. The radiation becomes gamma rays of immense energy. The black hole shrivels to quantum scales, where our classical description breaks down completely, and then it's gone, vanished. The event horizon winks out of existence, leaving behind only radiation, photons and perhaps other particles streaming away at the speed of light, carrying the black hole's mass energy off into the cosmos. What's left where the black hole used to be? According to classical evaporation theory, nothing. Just empty space and the outgoing radiation. The black hole has disappeared, and everything that ever fell into it, every star, every planet, every atom, every quantum of information, has been converted into thermal radiation. Thermal radiation, random structureless heat. The spectrum of Hawking radiation is thermal. It's described by the Planck distribution, the same formula that describes the radiation from a hot oven or a glowing coal. Thermal radiation carries no information about the source beyond its temperature. If you observe the radiation from a black hole evaporating, you learn its mass from the temperature and its rate of mass loss from the luminosity, but nothing else. You can't determine what fell into the black hole, what its quantum state was, what history led to its formation. And this is where the paradox reveals itself in full. Let's construct a thought experiment to make the problem concrete. Suppose you have two identical black holes, each with the same mass, charge, and spin. Into one black hole you drop a book, a physical copy of Shakespeare's collected works, bound in leather, containing the complete text of Hamlet, Macbeth, King Lear, all of it. Into the other black hole you drop a lump of coal with exactly the same mass as the book. According to general relativity and the no-hair theorem, the principle that black holes are characterized only by mass, charge, and spin, with no other distinguishing features, these two black holes are now identical. There's no way to tell them apart. The black hole that consumed Shakespeare looks exactly the same as the black hole that consumed coal. They have the same event horizon radius, the same gravitational field, the same response to external perturbations. Every observable property is identical. Now wait for both black holes to evaporate completely via Hawking radiation. According to the thermal nature of the radiation, both black holes emit exactly the same spectrum of photons and particles as they shrink and eventually disappear. The radiation from the Shakespeare black hole is indistinguishable from the radiation from the coal black hole. Once the evaporation is complete, both systems have been reduced to identical clouds of thermal radiation expanding into space. Where did the information go? The book contained information, the arrangement of letters on pages, the quantum states of every atom in the ink and paper. That information was encoded in the correlations between particles, the precise configurations that spelled out to be or not to be, and tomorrow, and tomorrow, and tomorrow. When the book fell into the black hole, that information crossed the event horizon and disappeared from the observable universe. Classically, we'd say the information is still inside the black hole, falling toward the singularity. But the black hole evaporated. It's gone, and the radiation it emitted was thermal, structureless, random, containing no trace of what fell in. the information appears to have been destroyed, not scrambled, not hidden, deleted from reality. This violates unitarity. Quantum mechanics says that information cannot be destroyed. The evolution of a quantum system is reversible. If you know the complete quantum state at one time, you can calculate the state at any other time, past or future. But if a black hole can destroy information, then the future state, thermal radiation, does not contain enough information to reconstruct the past state. Book plus black hole. The evolution is not reversible. Unitarity is violated. And if unitarity is violated, quantum mechanics collapses. The mathematical consistency of the theory depends on information conservation. Without it, you can create paradoxes. Energy can appear from nothing. Probabilities no longer sum to one. The entire framework that describes chemistry, atomic physics, quantum computing, all of it rests on the assumption that quantum evolution is unitary. So we face a stark choice. Either quantum mechanics is wrong, or general relativity is wrong, or something profound and unexpected happens to information near black holes that preserves it in a way we haven't yet understood. For decades, this was the information paradox, an apparent contradiction between two of our most successful physical theories, with no clear resolution. The paradox deepened when physicists examined the no-hair theorem more carefully. The theorem, proven in the 1960s and 70s by a series of mathematicians and physicists including Werner Israel, Brandon Carter, and David Robinson, states that black holes in general relativity are uniquely characterized by only three quantities: mass, electric charge, and angular momentum, spin. Nothing else. A black hole has no hair, no additional features that could carry information about what fell in. This is remarkable. If you drop a star into a black hole, the black hole's mass increases. If the star was rotating, the black hole's spin might change. If the star carried electric charge, though astrophysical objects are usually electrically neutral, the black hole's charge would change. But all the detailed information about the star, its composition, temperature, magnetic field, the arrangement of nuclei in its core, is lost. The black hole retains only those three numbers, M, Q, and J. The no-hair theorem makes sense from a classical perspective. Outside the event horizon, the gravitational field of a black hole is determined entirely by its mass, charge, and spin. General relativity's field equations guarantee this. Any additional structure, any hair on the black hole, would produce detectable features in the external gravitational field. But observations and theory both confirm that black holes are smooth, featureless, described by the Kerr or Reissner-Nordstrom metrics depending on their charge and spin. But quantum mechanically, this is disastrous. If a black hole has no hair, then all information about its interior is locked away behind the horizon, inaccessible to external observers. And when the black hole evaporates, emitting thermal radiation that depends only on mass, which determines temperature, there's no mechanism for that information to escape. It's gone. This isn't just a theoretical nicety. The information paradox has real consequences for our understanding of black hole thermodynamics, for the consistency of quantum field theory in curved spacetime, and ultimately for any attempt to formulate a quantum theory of gravity. If black holes can destroy information, then the laws of physics are fundamentally different inside and outside the horizon. The universe would be divided into regions where unitarity holds and regions where it doesn't. This is philosophically disturbing and mathematically inconsistent with how we believe physics should work. The crisis reached a head in the 1990s when debates about the paradox became contentious. Some physicists, including Hawking himself initially, argued that information genuinely is destroyed, that we need to modify quantum mechanics to allow for non-unitary evolution in the presence of black holes. Others, including Leonard Susskind and Gerard 't Hooft, argued fiercely that information must be conserved, that something in our understanding of black holes or quantum gravity must be wrong or incomplete. The stakes were high. This wasn't just an argument about black holes, it was about the fundamental structure of physical law. Can the universe forget? Can information be deleted? Or does reality maintain a perfect ledger, preserving every detail of every interaction for all time, even if scrambled beyond any practical hope of recovery? The resolution, when it finally emerged, required ideas so radical that they challenge our basic intuitions about space, dimensionality, and the nature of reality itself. The radiation pouring from a black hole is thermal. This single fact is the knife edge on which the paradox balances. Thermal radiation has a precise meaning in physics. It's the electromagnetic radiation emitted by any object in thermal equilibrium with its surroundings, radiation whose spectrum depends only on temperature. A lump of hot iron glows red because it's emitting thermal radiation with a peak wavelength, corresponding to its surface temperature. The sun radiates across the spectrum with a peak in visible wavelengths because its surface temperature is about 5,800 Kelvin. In each case, the radiation spectrum is described by Planck's law, a universal formula that connects temperature to the distribution of photon energies. Thermal radiation is, in a very specific sense, random. If you observe the photons coming from a hot object, their individual energies, directions, and polarizations are unpredictable. You can calculate the average energy, the total power emitted, the spectrum, but you cannot predict which specific photons will be emitted, when, or in which direction. The radiation is characterized entirely by statistical properties. It's a form of maximum entropy emission, the most disordered state of radiation possible for a given temperature. This randomness is why thermal radiation carries so little information. If you observe the glow from a hot coal, you can determine its temperature by measuring the spectrum. But you cannot determine what the coal is made of at the atomic level, how its atoms are arranged, what impurities it contains, or what its history was. All that fine-grained information has been thermalized, converted into heat and radiated away in a form that preserves only the bulk thermodynamic properties. Hawking radiation is thermal. It has a temperature inversely proportional to the black hole's mass, and it's emitted with a Planck spectrum characteristic of that temperature. This is what Hawking's calculations showed in 1974, and every subsequent analysis has confirmed it. To a distant observer, a black hole radiates like a perfect blackbody, an idealized object that emits thermal radiation with 100% efficiency. And this is where the paradox becomes acute. Because if Hawking radiation is truly thermal, then it carries no information about what fell into the black hole. The radiation depends only on the black hole's mass, which determines its temperature, and on how much mass the black hole has already radiated away. Nothing else. The photons and particles streaming from an evaporating black hole cannot encode information about the quantum state of the matter that fell in, because thermal radiation doesn't work that way. It's maximally random, maximally disordered, carrying the minimum possible information content. So when the black hole finally evaporates completely, having converted all its mass into outgoing Hawking radiation, what's left is a cloud of thermal particles expanding into space. And thermal particles, statistically described, cannot contain enough information to reconstruct what fell into the black hole billions of years earlier. The information has vanished. This is thermal amnesia. The black hole has forgotten what it consumed, and when it dies, it leaves behind only structureless heat. To understand why this is catastrophic for quantum mechanics, we need to think carefully about what unitarity means and why it matters. In quantum mechanics, the state of a system is described by a wave function, or more generally, by a state vector in a mathematical space called Hilbert space. This state vector encodes everything knowable about the system: the probabilities of measuring different outcomes, the correlations between different parts of the system, the phase relationships that determine interference effects. The evolution of this state vector over time is governed by the Schrödinger equation, which is deterministic and reversible. Reversibility means that if you know the state at any time t, you can calculate the state at any earlier time t or any later time t. The evolution is time-symmetric at the fundamental level. There's no inherent arrow of time in quantum mechanics. You can run the equations forward or backward and get consistent results. This reversibility is encoded in the mathematical structure of quantum theory through operators called unitary operators, which preserve the norm of the state vector and guarantee that probabilities sum to 1. Unitarity is not optional. It's built into the axioms of quantum mechanics. If you abandon unitarity, the entire mathematical framework becomes inconsistent. Probabilities no longer sum to 1, which means you can't interpret the theory as giving probabilities for measurement outcomes. Energy conservation can be violated. You could create energy from nothing by carefully manipulating non-unitary processes. Causality breaks down. Effects could be seen by causes because the time reversibility ensures consistent quantum structure is lost. The information paradox threatens unitarity at the most fundamental level. Suppose a pure quantum state is pure means the state is fully specified, not a mixture of different possibilities, but a definite quantum state with all phase relationships intact. This could be a carefully prepared quantum system, or it could be an ordinary object whose quantum state we've measured completely. The state falls into the black hole and crosses the event horizon. According to classical general relativity, it's now inside, causally disconnected from the outside universe. But quantum mechanically, the combined system, the black hole plus the infilling matter, is still in a pure state. Unitarity is preserved. The information describing the infilling matter now resides in the quantum state of the black hole plus interior matter. Now, the black hole begins to evaporate through Hawking radiation. If the radiation is purely thermal, then it's not in a pure quantum state. It's in a mixed state, a statistical ensemble of different possible states weighted by their thermal probabilities. A mixed state has less information than a pure state. It represents our ignorance about the system's true quantum state, described not by a single wave function, but by a density matrix that averages over many possible wave functions. And here's the problem. You cannot evolve a pure state into a mixed state through unitary evolution. It's mathematically impossible. Unitary evolution preserves the purity of states. If you start with a pure state and evolve it forward in time using the Schrödinger equation, you get another pure state. You cannot get a mixed state from unitary evolution of a pure state. But Hawking radiation is thermal, which means it's mixed. So if a pure state falls into a black hole, and the black hole radiates away as thermal Hawking radiation, the final state of the radiation is mixed. We've gone from pure to mixed. This violates unitarity. The evolution is not reversible. You cannot take the final thermal radiation and run the equations backward to reconstruct the initial pure state. The information has been destroyed. This is the crisis. Either information is destroyed, violating quantum mechanics, or something in our understanding is wrong. Hawking radiation cannot actually be perfectly thermal. or the evaporation process must preserve information in some subtle way we haven't yet understood, or our entire picture of what happens near the event horizon is flawed. The no-hair theorem makes the situation even worse. According to this theorem, proven rigorously in general relativity, a black hole is characterized entirely by three quantities: its mass m, its electric charge q, and its angular momentum j. That's it. No other properties. All the complexity of the matter that fell in, its composition, its quantum state, its history, is erased. The black hole retains only those three numbers. This theorem has been tested and verified through mathematical analysis and numerical simulations. If you throw a star into a black hole, the star's complex structure, its layers of different elements, its magnetic field, its rotation, its oscillations, all of this collapses down to contributions to M, Q, and J. After a short settling time during which gravitational waves carry away any excess asymmetries, the black hole becomes perfectly smooth and featureless. It's described by an exact solution to Einstein's equations: the Kerr-Newman metric if it has both charge and spin, the Kerr metric if it's uncharged but rotating, the Reissner-Nordström metric if it's charged but not rotating, or the Schwarzschild metric if it has neither charge nor spin. The exterior geometry is completely determined by M, Q, and J. There's no hair on the black hole, no additional features that could encode information about what fell in. This simplicity is beautiful from a mathematical standpoint. Black holes are the simplest macroscopic objects in the universe, described by just three numbers. But from a quantum information standpoint, it's terrifying. Think about how much information is contained in a star. Every atom has a position, a velocity, a quantum state. Every electron has a spin, every nucleus has an energy level. The number of quantum states a star can occupy is unimaginably vast, roughly 10 to the power of 10^1257 for a solar mass star. That's not a typo. 10 to the power of a number that's itself 57 digits long. The information content is astronomical in the most literal sense. When the star falls into the black hole, all of that information, 10^57 possible distinct quantum states, is reduced to three numbers. The information doesn't leak out gradually as the star crosses the horizon. It just vanishes from the external universe. From the perspective of an outside observer, it's as if the information has been deleted. The black hole's exterior gives no indication of what's inside beyond M, Q, and J. Classically, we'd say the information is still there, inside the black hole falling toward the singularity. It's not lost, just inaccessible. But the black hole evaporates. Eventually, through Hawking radiation, it will shrink and disappear completely. If the radiation is thermal, depending only on the mass at each moment, then when the black hole is gone, the information is truly lost. There's nowhere for it to hide. The no-hair theorem seems to leave no room for information to be encoded on the black hole's exterior. The theorem is rigorous, derived from the fundamental equations of general relativity. If it holds, and all evidence suggests it does, then a black hole cannot carry information about its interior in its external gravitational field or electromagnetic field. The only properties it has are M, Q, and J. So where could the information go? If it's not in the interior, which evaporates away, and it's not in the exterior because of no hair, and it's not in the Hawking radiation, which is thermal, then it must be destroyed. There's no fourth option, at least not in the framework of classical general relativity combined with quantum field theory in curved spacetime. The violation of unitarity has consequences beyond just information loss. It threatens the entire logical structure of quantum mechanics. Consider energy conservation. In quantum mechanics, energy conservation is a consequence of time translation symmetry through Noether's theorem. If the laws of physics are the same at all times, then energy is conserved. But energy conservation is intimately connected to unitarity through the structure of the Hamiltonian, the operator that generates time evolution. If unitarity is violated, the Hamiltonian cannot be a Hermitian operator, and energy conservation breaks down. This means that in a universe where black holes destroy information, energy could be created or destroyed. You could construct scenarios where matter falls into a black hole, carrying energy, and when the black hole evaporates, less energy comes out than went in. The missing energy hasn't gone anywhere. It's simply been deleted from the universe. Or worse, more energy could come out than went in, violating conservation from the other direction. Causality also becomes problematic. Quantum mechanics ensures causal structure through the commutation relations between operators at space-like separated points. These commutation relations guarantee that measurements in one location cannot instantaneously affect measurements at a distant location. But if evolution is non-unitary, these relations break down. You could have causal paradoxes, effects preceding causes, or influences propagating faster than light. The interpretation of quantum mechanics itself becomes incoherent. What does it mean to assign a probability to a measurement outcome if probabilities don't sum to 1? The Born rule, which tells us how to calculate probabilities from wave functions, assumes unitary evolution. Without unitarity, the Born rule fails. We lose the ability to make predictions, to connect theory with experiment, to use quantum mechanics at all. This is why the information paradox mattered so much to physicists in the 1980s and 90s. It wasn't an obscure technical detail. It was a fundamental threat to the consistency of quantum theory, one of the most successful and thoroughly tested theories in the history of science. If black holes really destroy information, then quantum mechanics as we know it is wrong. Not just incomplete or approximate, fundamentally wrong in a way that requires radical revision. The battle lines were drawn. On one side stood those, including Hawking initially, who argued that black holes genuinely destroy information, that we need to modify quantum mechanics to accommodate non-unitary evolution in gravitational contexts. On the other side stood those, including Susskind and T. Hooft, who insisted that information must be conserved, that something in our understanding of black holes must be incorrect or incomplete. The debate was fierce, sometimes personal, extending over decades. It was fought in technical papers, at conferences, in popular books. At stake was not just the resolution of a paradox, but the future direction of theoretical physics. Would we abandon unitarity, one of quantum mechanics' foundational principles? Or would we find a way to reconcile black hole evaporation with information conservation, even if it required ideas that seemed impossible? The answer, when it came, emerged from a completely unexpected direction. Not from detailed calculations of Hawking radiation, not from new observations of black holes, but from thinking about entropy, area, and the strange possibility that the three-dimensional world we inhabit might be a hologram. In 1972, a graduate student named Jacob Bekenstein proposed something that seemed absurd. He suggested that black holes have entropy. Entropy, in thermodynamics, is a measure of disorder, the number of microscopic configurations that correspond to the same macroscopic state. A gas at a given temperature and pressure can have its molecules arranged in countless different ways, all of which look the same from a macroscopic perspective. The entropy counts those possibilities. More configurations mean higher entropy. It's a measure of how much information is hidden in the microscopic details, information that doesn't affect the observable bulk properties. Bekenstein's proposals seem to violate a fundamental principle. The second law of thermodynamics states that the total entropy of a closed system can never decrease. It can stay the same in reversible processes or increase in irreversible ones, but it cannot go down. This law is one of the most ironclad in physics, more certain than Newton's laws or even energy conservation in some contexts. It defines the arrow of time, the direction in which physical processes naturally evolve. But black holes appeared to violate the second law. Consider a thought experiment. Take a box of hot gas which has entropy proportional to the number of molecules and their temperature. Now throw the box into a black hole. The box and its contents disappear behind the event horizon. From the outside, the entropy of the universe appears to have decreased. The hot gas had entropy, and now it's gone, hidden behind the horizon where it can't affect anything external. Bekenstein's solution was radical: assign entropy to the black hole itself. When the box of gas falls in, the black hole's entropy increases, compensating for the apparent loss of the gas's entropy. The total entropy, gas plus black hole, doesn't decrease after all. The second law is saved, but at the cost of attributing thermodynamic properties to objects that, according to classical general relativity, are completely simple and featureless. Bekenstein went further. He proposed a formula for black hole entropy, arguing from dimensional analysis and theoretical consistency that it should be proportional to the area of the event horizon. Not the volume, the area. This was strange. Normally, entropy is an extensive quantity, scaling with volume. A box twice as large holds twice as many gas molecules and has twice the entropy. But Bekenstein's formula said black hole entropy should scale with area, not volume. The formula he derived, refined by Hawking and others, is now called the Bekenstein-Hawking entropy. S relativity Kc3 4g xa, where K is Boltzmann's constant, C is the speed of light, is the reduced Planck constant, G is the gravitational constant, and A is the area of the event horizon. The prefactor has a value close to 1 in Planck units, making the formula remarkably simple. Entropy equals area divided by 4 times the Planck area, which is the smallest meaningful area in quantum gravity, roughly 1070 square meters. For a solar mass black hole with an event horizon radius of about 3 kilometers, the area is about 1014 square meters. Plugging this into Bekenstein's formula gives an entropy of about 1077 in dimensionless units, an enormous number. For comparison, the entropy of the Sun, if it were in thermal equilibrium, would be around 1058. The black hole has far more entropy than the star it collapsed from, which seems contradictory until you realize the entropy measures the number of possible quantum states consistent with the macroscopic properties. But what are those states? What microscopic degrees of freedom give rise to this enormous entropy? For a gas, entropy counts molecular arrangements. For a crystal, it counts lattice vibrations and defects. What does black hole entropy count? The event horizon has no structure in classical general relativity. It's a purely geometrical surface, not made of anything. There are no molecules to rearrange, no vibrations to excite. The entropy formula seems to count something that doesn't exist. This question haunted theorists for decades. Black hole entropy was derived from thermodynamic arguments and confirmed by Hawking's calculation of black hole temperature. Objects with temperature must have entropy, and the relationship between the two is fixed by thermodynamics. But the physical origin of the entropy, the microscopic states being counted, remained mysterious. The answer would eventually come from string theory and quantum gravity. But before we get there, we need to understand the profound implication of entropy scaling with area rather than volume. The fact that black hole entropy is proportional to area suggested something deeply strange about how information is stored in systems with strong gravity. In ordinary physics, information is stored throughout the volume of a system. A book's information is in the ink molecules, scattered across pages throughout the book's three-dimensional volume. A computer's memory is in the spin states of electrons distributed through the three-dimensional structure of its chips. But black hole entropy scaling with area suggested that all the information about what fell into a black hole, potentially encoding the quantum states of an entire star or galaxy, is stored not in the volume within the event horizon, but somehow on the two-dimensional surface of the horizon itself. This seemed impossible. How can a three-dimensional volume of information be encoded on a two-dimensional surface? It's like claiming you could store an entire library, not in a three-dimensional building, but painted onto a flat wall. There isn't enough room. Or is there? Gerard at Hooft, in a speculative paper in 1993, suggested that the universe might work like a hologram. In holography, the technology that produces three-dimensional images on two-dimensional films, information about a three-dimensional scene is encoded in interference patterns on a flat surface. When you illuminate the holographic film correctly, the three-dimensional image reconstructs itself. De Hooft proposed that something similar might happen with black holes. All the information about the three-dimensional interior might be encoded in quantum states on the two-dimensional event horizon. Leonard Susskind developed this idea further, formalizing what became known as the holographic principle. The principle states that the maximum amount of information that can be contained in a spatial region is proportional not to the volume of the region, but to the area of its boundary. This applies universally, not just to black holes. Every region of space has an information limit set by the area of its surface, measured in Planck units. This is profoundly counterintuitive. It suggests that three-dimensional space, as we perceive it, might not be fundamental. The fundamental reality might be two-dimensional, a surface encoding quantum information, and the three-dimensional world we experience might be a kind of projection or emergent phenomenon arising from the information on that surface. Think of it this way. Imagine you're a character in a video game. From your perspective inside the game, the world is three-dimensional. You can move forward and backward, left and right, up and down. The world has depth, volume, spatial extent. But from the perspective of the computer running the game, all the information describing your world is stored in the computer's memory. Essentially, a two-dimensional array of bits. The three-dimensional world you perceive is reconstructed from that two-dimensional data structure. The 3D world is emergent, a user interface generated from underlying 2D information. The holographic principle suggests our universe might work similarly. Not that we're literally in a simulation, that's a separate question, but that the fundamental description of reality might be in terms of information on a boundary, with the three-dimensional space-time we inhabit being an emergent holographic projection from that boundary. This idea gained substantial support from developments in string theory, particularly the ADA-CFT correspondence discovered by Juan Maldacena in 1997. This is a precise mathematical relationship between a theory of quantum gravity in a space with negative curvature, called anti-de Sitter space, or ADS, and a quantum field theory without gravity living on the boundary of that space, a conformal field theory, or CFT. The correspondence is exact and holographic. Everything happening in the higher dimensional gravitational bulk can be described by a theory on the lower dimensional boundary. ADS-CFT gave physicists a concrete example where the holographic principle is not just philosophy, but rigorous mathematics. It provided a dictionary translating between gravitational physics in the bulk and quantum field theory on the boundary. black holes in the bulk correspond to thermal states in the boundary theory. Information that appears to be lost in the bulk black hole evaporation is manifestly conserved in the boundary theory, which obeys standard unitary quantum mechanics. The correspondence doesn't directly describe our universe. We don't live in ad space, but it proved that holography can work in principle. It showed that a gravitational theory in n dimensions can be exactly equivalent to a non-gravitational quantum theory in n1 dimensions. The universe might genuinely be holographic, with three-dimensional space emerging from more fundamental two-dimensional physics. If the holographic principle is correct, then the information paradox has a resolution, at least in principle. When matter falls into a black hole, the information doesn't vanish into an inaccessible interior. It's encoded on the event horizon itself, distributed across the horizon's area in quantum states that we don't yet fully understand, but that must exist if black hole entropy is real. As the black hole evaporates through Hawking radiation, the information stored on the horizon is gradually released into the radiation. The radiation isn't perfectly thermal. It can't be if information is conserved. There must be subtle correlations in the radiation, deviations from perfect thermality that encode information about what fell in. These deviations would be incredibly small, effectively invisible to any realistic measurement, but they must be there if unitarity is preserved. This is the beginning of the resolution. The holographic principle tells us that information can be stored on the horizon in a way that classical general relativity doesn't account for. AID-S CFT proves that such holographic storage is possible in at least some gravitational theories. But these are still abstract ideas, and they don't yet provide a detailed mechanism for how information escapes during evaporation. For that, we need to dig deeper into the quantum structure of space-time itself, into the possibility that space and time are not fundamental, but emergent from something more basic. We need to understand how quantum entanglement, the strange correlations between distant quantum systems, might be the fundamental building block from which space-time geometry arises. Because the latest breakthrough in understanding the information paradox comes from realizing that space-time and entanglement are intimately connected, that the geometry of space might literally be made of quantum entanglement, woven from the correlations between quantum fields. This idea, encapsulated in the slogan, "Entanglement builds geometry," has led to the most promising resolution of the information paradox yet discovered. Quantum entanglement is one of the strangest features of quantum mechanics. When two particles are entangled, measuring one particle instantaneously affects the other, regardless of the distance separating them. This doesn't allow faster-than-light communication. The correlations only become apparent when you compare measurement results later. But it creates a connection between particles that has no classical analog. Einstein called it spooky action at a distance and considered it evidence that quantum mechanics was incomplete. But experiments have confirmed entanglement countless times. It's real, it's fundamental, and it's essential to the structure of quantum theory. In the context of quantum field theory, entanglement is ubiquitous. The vacuum state of a quantum field is highly entangled. Different regions of space are correlated in intricate ways. When you separate two regions and ask how entangled they are, the answer depends on the area of the boundary between them. The entropy of entanglement, a measure of how strongly the regions are correlated, scales with the area separating them. This area scaling of entanglement entropy is exactly analogous to the area scaling of black hole entropy. And it's not a coincidence. In the mid-2000s, physicists began to suspect that space-time geometry and quantum entanglement might be two sides of the same coin. That the smooth, curved space described by general relativity might emerge from the entanglement structure of underlying quantum fields. Mark van Ramsdonk, working with ideas from string theory, showed that in ADS CFT, cutting entanglement in the boundary theory corresponds to tearing apart spacetime in the bulk theory. If you take a system described by the boundary CFT and gradually reduce the entanglement between two halves, the corresponding bulk spacetime develops a growing separation between the two regions. When entanglement is completely severed, the bulk spacetime splits into disconnected pieces. Entanglement literally holds space together. This led to the ER-EPR conjecture, proposed by Maldacena and Susskind. ER refers to Einstein-Rosen bridges, wormholes connecting distant regions of spacetime. EPR refers to Einstein-Podolsky-Rosen entanglement, quantum correlations between distant particles. The conjecture states that these are the same thing. Entangled particles are connected by tiny, non-traversable wormholes in spacetime geometry. The quantum connection is also a geometric connection. If this is true, then spacetime is emergent. The fundamental reality is quantum information, quantum states, and their entanglement structure. Spacetime geometry, the smooth manifold with its metric and curvature that we describe with general relativity, is an approximate, coarse-grained description of this underlying quantum information. At the Planck scale, where quantum gravity effects become important, spacetime might dissolve into something more fundamental, a network of quantum correlations without smooth geometry at all. This emergent spacetime picture has profound implications for the information paradox. If spacetime is made of entanglement, then the interior of a black hole and the exterior are not as separate as they seem. They're entangled. The quantum state of matter inside the black hole is correlated with the quantum state of Hawking radiation outside. As the black hole evaporates, these correlations become more and more important, eventually dominating the geometry. The picture emerging from recent work is that the black hole interior and the Hawking radiation are not two separate systems, but different descriptions of the same quantum information. What appears from one perspective as matter inside the black hole appears from another perspective as outgoing radiation. The information isn't trapped inside and then destroyed. It's present in both descriptions simultaneously, encoded in the entanglement structure connecting interior and exterior. This might sound like word games, but it's grounded in precise mathematical calculations, particularly in the context of ADS CFT and related holographic theories. The interior of the black hole is not an independent region of spacetime, but an emergent description arising from entanglement between degrees of freedom on the boundary. When you account for this correctly, information is never lost. It's encoded in subtle correlations in the radiation, correlations that reflect the quantum state of everything that fell in. The three-dimensional space we live in might be a hologram projected from information on a distant, two-dimensional surface. The interior of a black hole might not be a separate place, but an emergent description of quantum information already present in the radiation. Space and time themselves might not be fundamental, but constructed from the entanglement of underlying quantum fields. These ideas sound like science fiction. They challenge basic intuitions about reality, locality, and the structure of space. But they emerge inevitably from taking seriously the combination of general relativity, quantum mechanics, and the thermodynamic properties of black holes. If the universe is to be mathematically consistent, if information is to be conserved, something this radical appears necessary. And in the past few years, these abstract ideas have led to concrete calculations that finally resolve the information paradox in specific contexts. The resolution comes from recognizing that the interior of an evaporating black hole contains regions called quantum extremal islands that are actually part of the radiation system, entangled with the outgoing Hawking radiation in ways that preserve information. Let's see how this works. In 1993, a physicist named Don Page made a prediction that would take nearly 3 decades to fully understand. Page was working on the quantum mechanics of black hole evaporation, trying to trace what should happen to entanglement as a black hole radiates. He assumed as a starting point that information is conserved, that the process is ultimately unitary, even if we don't understand the mechanism. Under this assumption, he calculated how the entropy of the Hawking radiation should evolve over time as the black hole shrinks. The result was a curve that now bears his name, the Page curve. It shows the entropy of the radiation as a function of time, and its shape is distinctive and surprising. Initially, as the black hole begins to evaporate, the entropy of the radiation increases. This makes intuitive sense. More radiation is being emitted, so the entropy should grow. The radiation at this stage appears to be maximally entangled with the black hole's interior, carrying no information about what fell in. It's thermal, random, structureless. The entropy climbs steadily, but at a specific moment, the Page time occurring when the black hole has evaporated roughly half its initial mass, something remarkable happens. The entropy of the radiation stops increasing and begins to decrease. From this point forward, as more radiation is emitted and the black hole continues to shrink, the total entropy of the radiation drops. By the time the black hole has completely evaporated, the radiation's entropy returns to exactly the value it had before the black hole formed. This decrease seems impossible at first glance. How can emitting more radiation decrease the radiation's total entropy? The answer lies in quantum entanglement. After the Page time, the newly emitted Hawking radiation is no longer maximally entangled with the black hole. Instead, it's entangled with the previously emitted radiation. The old radiation and the new radiation share quantum correlations that reduce the total entropy of the radiation system. Think of it this way. Early in evaporation, each photon of Hawking radiation is uncorrelated with the others, random, thermal, contributing to increasing entropy. But after the Page time, the photons start becoming correlated with each other. They're still individually random, but there are subtle relationships between them, patterns that wouldn't exist in purely thermal radiation. These correlations encode information. As more correlated photons are emitted, they purify the radiation state, reducing its entropy. By the end of evaporation, the radiation is in a pure quantum state, a specific configuration that encodes all the information about what originally fell into the black hole. The information was never destroyed. It was scrambled, distributed across countless photons emitted over the black hole's lifetime, but it's still there. If you could somehow measure all the photons with perfect precision and perform an impossibly complex calculation, you could reconstruct the quantum state of everything that fell in. This is a beautiful picture, and it's consistent with unitarity. The Page curve shows that information conservation is possible in principle, but for decades it was just a conjecture. Page assumed unitarity and calculated what should happen if information is conserved, but he didn't provide a mechanism. He couldn't explain how the radiation becomes entangled with itself rather than with the black hole. The mechanism remained a mystery until 2019. The breakthrough came from thinking carefully about entropy calculations in theories with gravity, using tools from the holographic principle and quantum gravity. In 2019, a series of papers by Jeff Pennington, Ahmed Almhairi, Netta Engelhardt, Henry Maxfield, and others showed that when you calculate entropy correctly in gravitational theories, you have to account for something unexpected: quantum extremal surfaces. These are surfaces in space-time whose area, plus the entropy of quantum fields on one side of the surface, is minimized. The true entropy of a region is given by finding the quantum extremal surface and computing its generalized entropy. The key insight is that these extremal surfaces can jump. Early in black hole evaporation, the quantum extremal surface sits just outside the event horizon. The entropy calculation includes the black hole's Bekenstein-Hawking entropy, proportional to the horizon area, plus the entropy of radiation outside. As the black hole radiates and shrinks, the horizon area decreases, but the radiation entropy increases. But at the page time, something dramatic happens. The quantum extremal surface jumps discontinuously. Instead of hugging the event horizon, it now extends into the black hole's interior, enclosing a region inside the horizon and connecting to the distant radiation. This interior region is called a quantum extremal island, or simply an island. The island is, geometrically, inside the black hole's event horizon. Classically, it's causally disconnected from the exterior universe. Nothing inside can send signals out. But quantum mechanically, through the entanglement structure of quantum fields, the island is actually part of the radiation system. The quantum state of fields on the island is entangled with the quantum state of the Hawking radiation far outside. This is where the information lives. Before the page time, there are no islands. The quantum extremal surface is just the black hole horizon, and the radiation appears to be thermally entangled with the black hole interior. But after the page time, islands form. The information about what fell into the black hole is encoded in the quantum state on these islands, which are entangled with the radiation. As the black hole evaporates further, the islands grow, eventually encompassing the entire black hole interior. At the moment of complete evaporation, all the information has been transferred to the radiation. The page curve is reproduced exactly. The entropy of the radiation increases, reaches a maximum at the page time, then decreases back to zero as the black hole vanishes. Information is conserved. Unitarity is preserved. This might sound like mathematical sleight of hand. How can something inside the event horizon, causally disconnected from the outside, be part of the radiation system? The answer comes back to the holographic principle and the emergent nature of space-time. The interior of the black hole is not a fundamental region of space. It's an emergent description arising from quantum entanglement in the fundamental holographic theory. What we call the interior and what we call the radiation are two different ways of describing the same underlying quantum information. Islands represent the transition between these perspectives. Early in evaporation, the interior description is useful. There's a large black hole with an interior space-time. Geometry. Late in evaporation, the radiation description is useful. There's no black hole, just radiation carrying all the information. At intermediate times, both descriptions partially apply, and the island prescription tells you how to combine them correctly. The mathematics works out because of deep properties of quantum entanglement and gravity. In holographic theories, the entanglement structure of quantum fields determines the space-time geometry. The islands are determined by minimizing the generalized entropy, a procedure that follows from the fundamental principles of quantum gravity. This resolution has been worked out rigorously for certain simplified models of black holes, particularly in two-dimensional spacetime with holographic duals. The page curve emerges exactly as predicted. Information is conserved. The radiation, while appearing thermal locally, contains subtle long-range correlations that encode everything that fell in. Whether this picture applies to realistic, four-dimensional black holes remains an open question. The full theory of quantum gravity for our universe doesn't exist yet. But the conceptual breakthrough is clear. Information is not destroyed by black holes. It's scrambled beyond any practical hope of recovery, distributed across radiation emitted over timescales longer than the current age of the universe, encoded in correlations so subtle they're effectively invisible. But it's there. Let's return to our thought experiment with the book and the coal. You drop Shakespeare's complete works into a black hole. Someone else drops an identically massed lump of coal into an identical black hole. Both black holes evaporate completely over 10 or 67 years. Does the radiation carry information about what fell in? According to the island prescription, yes. The radiation is not perfectly thermal. There are deviations, tiny, unmeasurable with any conceivable technology, but real, that encode the quantum state of the book versus the coal. If you could collect every single photon emitted during the entire evaporation, measure all their properties with perfect precision, and perform a calculation of unimaginable complexity, you could, in principle, reconstruct whether the black hole consumed Shakespeare or carbon. This is what we mean by saying information is scrambled, not deleted. The information hasn't been destroyed, but it's been processed through the most efficient scrambler in the universe. The black hole takes the orderly information in the book, letters arranged in words in sentences, and spreads it across 10^77 or more quantum states on the event horizon, then radiates it out in a form where recovering it would require correlating 1067 years worth of photons with Planck scale precision. For all practical purposes, the information is lost. No civilization could perform the measurement and calculation required to decode it. The resources required would dwarf the entire observable universe. The information is there, but it's functionally inaccessible. The universe remembers. But what it remembers is hidden in a code we can never break. The paradox is resolved. Information is not destroyed, it's preserved in the quantum state, transferred gradually from the black hole to the radiation through quantum extremal islands that straddle the boundary between interior and exterior. The universe's memory is intact, even when scrambled beyond all hope of recovery. The universe will not end with fire. It will end with a slow fade into absolute darkness, a descent toward maximum entropy that takes timescales so vast they render the current age of the cosmos, 13.8 billion years, barely our opening moment. We live in what cosmologists call the stelliferous era, the age of stars. Galaxies shine. Nuclear fusion converts hydrogen into helium in stellar cores, releasing energy that lights up the universe. Planets orbit their suns. Life, at least on one small world, has emerged to contemplate its cosmic context. This era began a few 100 million years after the Big Bang, when the first stars ignited, and it will continue for trillions of years more as the last red dwarfs, small cool stars that burn their fuel parsimoniously, exhaust their hydrogen, and fade. But the stelliferous era is temporary. Eventually, star formation will cease. The gas needed to make new stars will be locked up in stellar remnants, white dwarfs, neutron stars, black holes, or dispersed so widely by cosmic expansion that it never condenses. The galaxies will go dark, one star at a time, over timescales measured in tens of trillions of years. And when the last star dies, the universe will enter the black hole era. This is when black holes dominate the cosmic inventory of mass. Everything else, planets, asteroids, the cold remnants of dead stars, will either fall into black holes or drift in isolation through expanding space. The black holes themselves will be all that remains of the great structures of the universe, the final condensed matter holding out against the relentless pull toward maximum entropy. And then, given enough time, even the black holes will evaporate. The timescales are difficult to comprehend. A solar mass black hole evaporates in approximately 10^67 years. That's a 1 followed by 67 zeros. To put this in perspective, the universe is currently 1.4 ik 10 years old. The ratio between a black hole's evaporation, time, and the current age of the universe is roughly 10^57, a number so large that there are more years in a black hole's lifetime than there are atoms in your body. For supermassive black holes like Sagittarius A, the timescale extends to approximately 10^999 years. These are Google-scale timescales, numbers that approach the etymological origin of Google itself, the number 10^100, invented by a 9-year-old to represent something unimaginably large. During the vast majority of this time, almost nothing happens. The black hole sits in space, radiating photons so rarely that you might wait billions of years between emissions. The temperature is effectively zero, far colder than the cosmic microwave background that currently bathes the universe at 2.7 Kelvin. The black hole is darker than the darkness around it, a gravitational well emitting faint quantum whispers into the void. But the evaporation is inexorable. Each photon carries away energy, reducing the black hole's mass, and as the mass decreases, the temperature rises. Hawking's formula, temperature inversely proportional to mass, means that smaller black holes are hotter. The process accelerates. When a solar mass black hole has evaporated down to 1/10 of its original mass, it's 10 times hotter and radiating 100 times faster. The timeline compresses. By the time it's shrunk to Earth's mass, it's hot enough to glow in infrared. When it weighs as much as a large asteroid, 1 trillion kilograms, it radiates invisible light, shining like a distant star against the ancient darkness. At 1 billion kilograms, it's blazing in X-rays with the luminosity of a supernova. And then comes the final second. The last moments of a black hole's existence are violent beyond description. As the mass approaches zero, the temperature skyrockets toward infinity. The event horizon shrinks to quantum scales, where our classical description of space-time breaks down completely. The black hole pours out its remaining mass energy in a catastrophic burst of radiation, gamma rays of immense energy, perhaps even exotic particles created in the extreme temperatures near the Planck scale. The power output in those final moments exceeds anything in the observable universe. For a fraction of a second, this dying black hole, now weighing less than 1 kilogram, smaller than an atom, outshines entire galaxies. The radiation spectrum extends to energies where quantum gravity effects dominate, where space and time themselves might dissolve into something more fundamental. What happens at the very end? When the black hole reaches the Planck mass, about 22 micrograms, the mass where gravitational effects become quantum mechanically important. Does it disappear smoothly, radiating its last energy and leaving nothing? Does it leave behind a remnant, some stable quantum gravitational object that can't evaporate further? Does it tunnel quantum mechanically into something else entirely, perhaps creating a new baby universe branching off from ours? We don't know. The final fate of an evaporating black hole lies in the domain of quantum gravity, where we have theories but no confirmed framework. String theory, loop quantum gravity, and other approaches make different predictions. Experiments are impossible. We cannot create or observe Planck-scale physics in any laboratory or telescope. The question remains open, a mystery that might not be resolved until we have a complete theory of quantum gravity. But whatever happens in that final instant, the result is the same from the perspective of the larger universe. The black hole vanishes. The event horizon winks out of existence. What remains is radiation, photons and particles streaming away at the speed of light, carrying the black hole's mass energy off into the expanding cosmos. And that radiation, as we've learned, carries information. The scrambled quantum state of everything that ever fell into the black hole is encoded in correlations between those particles, preserved even as it scattered across light years and light centuries. The universe has not forgotten. It has simply encrypted its memories in a form so complex that decoding them would require more computational power than the universe can supply. Eventually, every black hole will evaporate. The stellar mass black holes formed from collapsed stars, the intermediate mass black holes lurking in dense star clusters, the supermassive and ultramassive black holes anchoring galaxy centers. All of them will radiate away their mass and disappear. The timeline varies. Small black holes go first, vanishing in the relatively early universe, still trillions upon trillions of years in the future, but soon compared to the supermassive giants. The supermassive black holes are last, holding out for 100 years or more, the final complex structures resisting the universe's slide toward equilibrium. Imagine you could watch the universe in fast forward, compressing those unimaginable timescales into something comprehensible. The stars blink out like candles in a gentle wind. Galaxies fade to darkness, their stars exhausted or swallowed. Black holes float in an expanding void, separated by distances that grow without bound as space stretches. One by one, starting with the smallest, they evaporate in brief flares of radiation. The flares become less frequent as only the larger holes remain, spaced farther and farther apart. Finally, the last black hole, perhaps a supermassive giant that once anchored a galaxy cluster, evaporates in solitude. Its final burst of radiation spreads into space, joining the dilute sea of photons from all the black holes that came before. The universe is left with nothing but radiation expanding and cooling, spreading thinner with every passing eon. This is the heat death of the universe. The final equilibrium state toward which everything has been trending since the Big Bang. Maximum entropy. No structure, no gradients, no differences in temperature or density that could drive processes or enable complexity. Just a thin, cold bath of radiation, growing more diffuse without limit as space expands forever. The temperature asymptotically approaches absolute zero. The distance between any two photons grows toward infinity. The universe becomes a perfect void, empty and still, with nothing left to change and nowhere left to go. The story ends not with a bang, but with silence, eternal, absolute, and complete. This far future scenario assumes our current understanding of cosmology is correct, that dark energy drives accelerated expansion, that the universe will expand forever, that no unknown physics intervenes. These assumptions might be wrong. The nature of dark energy remains mysterious. Perhaps it will decay or change properties, altering the expansion history. Perhaps quantum fluctuations or tunneling events will trigger new phases of cosmic evolution we can't currently predict. But if our current models hold, the heat death is inevitable. The second law of thermodynamics, entropy always increases in closed systems, drives the universe relentlessly towards this maximum entropy state. Every process that occurs from star formation to black hole evaporation increases the total entropy. The universe is running down, converting ordered energy into disordered heat, moving from complexity toward simplicity, from structure toward uniformity. And yet, even in this bleak far future, the universe retains its memory. The information describing every particle that ever existed, every interaction that ever occurred, every life that ever arose. All of it persists in the quantum correlations between photons scattered across the infinite void. Scrambled, inaccessible, meaningless to any possible observer. but preserved in accordance with the laws of quantum mechanics. The universe does not forget, even when there is nothing left to remember and no one left to ask.